Hello, my name is Juan Carlos García Altamirano, and I'll be talking about computational complexity of Hajós constructions of symmetric odd cycles. This research was done in collaboration with Mika Olsen and Jorge Cervantes. Well, let's start. A digraph T is a finite non-empty set V of vertices and a set A or ordered pairs of distinct vertices called arcs. If U and V are vertices and there is or isn't an arc between U and V, we say they are adjacent or not adjacent. Here there are two not adjacent vertices, and here there are two adjacent vertices with the arc UV. An arc UV is symmetric if VU is also an arc. Here we have a symmetric arc between the vertices U and V. A digraph D is symmetric or bidirected graph if every arc of D is a symmetric arc, like in here. The symmetric digraph DG of the graph G is the digraph of chain by replacing each edge of G with a symmetric arc. This is the complete graph K3, while this is the symmetric complete digraph DK3. This is the cycle of length 5, while this is the symmetric cycle of length 5. An acyclic coloring of the digraph D is a vertex coloring of D such that D has no monochromatic directed cycles. For example, in this digraph, these two vertices cannot have the same color due to this symmetric arc, but this tree can, and this tree can too. This other vertex cannot has the red color due to this directed cycle, neither the blue color due to this directed cycle. So in this coloring, we need a new color for it. However, there is an acyclic coloring with two colors, as shown in here. Then we define the dichromatic number. The dichromatic number of a digraph D is the minimum number of colors on a cyclic coloring, denoted by DCD. A digraph D is K-critical if its dichromatic number is K and the dichromatic number for every proper subdigraph of D is minor to K. For example, this digraph has dichromatic number 3, but if we remove any arc, the dichromatic number is smaller. I talk about the two Hajós operations. One operation is the identification of not adjacent vertices. Let D be a digraph. Let X be a set of not adjacent vertices of D, and let V be a new vertex, or one of the vertices of X. We define the identification of X in V by identify all vertices of X in V by dragging their adjacencies, as shown in the following animation. Note that this diagram has dichromatic number 2. We identifying these two not adjacent vertices, and we identifying these two not adjacent vertices. Now, this diagram has dichromatic number 3. If the diagram H was obtained by identifying a set of not adjacent vertices of D, then the dichromatic number of D is less than or equal to the dichromatic number of H. Due to an acyclic coloring of the vertices of H induce an acyclic coloring of the vertices of D. The other Hajós operation is the directed Hajós join. The directed Hajós join is defined as, here there are two disjoint digraphs, the 1 and the 2. We select an arc U1, V1 of the 1, and an arc U2, U2 of the 2. Delete them. Add a new arc U1, U2, and finally, we identifying the vertices V1 and V2. just like that. In 2020, Van Jensen et al. Proved in the paper called Hajós and other constructions for diagrams that we can construct each K-critical diagram with directed Hajós joins and identification of not adjacent vertices from copies of the symmetric complete diagram of order K. In that paper, they left the following as an open question. How can a symmetric cycle of length phi be constructed from copies of the symmetric complete diagram of order 3 by only using directed Hajós joins and identification of not adjacent vertices? We answered that question. We adapted a generic algorithm to solve this problem. The directed Hajós join became the recombination operator, and the identification of not adjacent vertices became the mutation operator. This algorithm obtained a sequence of Hajós operations that went through more than 5,000 generations. However, we reduced that sequence to 16 Hajós operations. We start with a directed Hajós join of two copies of TK3. Delete this arc and delete this arc too. Add this arc and identifying this vertex with this vertex. Then, with the resulting diagram, we do another directed Hajós join with two copies of it with these arcs. Delete these two arcs, add this arc, and identifying this vertex with this vertex. And at the same time, identifying this with this, and so consecutively, resulting this symmetric cycle of length 5 with two extra arcs. We do a convolute rotation, and then we do another directed Hajós join with two copies of it with these arcs. Delete these two arcs, add this arc, and identifying this vertex with this vertex, and identifying this with this, and so on, resulting this symmetric cycle of length 5 with one extra arc. Finally, we do another directed Hajós join with two copies of it with these arcs. Delete this arc, add this arc, and identifying this vertex with this vertex, and identifying this with this, and so consecutively, resulting this symmetric cycle of length 5. This is the answer that Pat Jensen question. We realized that with a similar procedure, we can construct the symmetric cycle of length 9, as shown in the following animation. In general, with a cycle of this length, we can construct a cycle of this length. That is, with this construct this, and with this construct this, and with this construct this, and so on. For the other odd cycle of shorter length, we do extra identification. For example, to construct the cycle TC13, we identify these three vertices, and then we identify these three vertices. With our procedure, the number of operations that we do to construct a symmetric odd cycle of length n from dk3 is between this and this. Therefore, its computational complexity is theta n times natural logarithm of n. Thank you for your attention. Any question or remark, please write in this email. These are the references.